Hello, this is Professor Kuehn, and welcome back to my lectures on electricity, magnetism, and light. We're looking at Tyndall's lectures on light, and we are on page 260 in A Student's Guide to the Grade Physics Texts, Volume 3. So I'm going to read the first paragraph here in the section that we are on. And here Tyndall says that the double refraction of Iceland's spar was first treated in a work published by Erasmus Bartholinus in 1669. He goes on to say that the celebrated Huygens sought to account for this phenomenon on the principles of the wave theory, and he succeeded in doing so. He, moreover, made highly important observations on the distinctive character of the two beams transmitted by the spar, admitting, with resigned candor, that he had not solved them and leaving that solution to future times. So there, on the one hand, Huygens' theory was able to account for some aspects of birefringence, but not entirely. That is, it was unsatisfactory. He goes on to say that Newton, so here, remember what Tyndall's doing is kind of comparing and contrasting Huygens and Newton's theories. He says Newton, reflecting on the observations of Huygens, came to the conclusion that each of the beams transmitted by Iceland's spar had two sides, and from the analogy of his two-sidedness with the two-endedness of magnets, wherein consists its polarity, the two beams came subsequently to be described as polarized. So he's reminding us that Newton talked about in his particle theory of light that the individual particles of light behaved a bit like little magnets in the sense that they had two different sides, one end and another. He called them polarized, and that's where our language of polarization of light comes from. And now what Tyndall is going to do is he's going to develop his thinking about the polarization of light, and he's going to explain how if one understands that light is a transverse wave rather than a longitudinal wave, as Huygens erroneously thought, then one is able to account for the birefringence of Iceland's spar. So let's talk about what he is discussing in the next couple of pages. And he's going to be using what is called tourmaline. And tourmaline is a particular kind of crystal occurring in nature, and it acts as a natural polarizing filter. That is, it allows vibrations of light that are transversely oriented in one orientation to pass and attenuates the other. So let me make a drawing here. So let's suppose that, let me draw a different color. Let's suppose that I draw a coordinate system like this. It's always helpful to start with a coordinate system so it makes it easier to communicate about the orientations of things. So I'm going to draw an X, Y, and Z axes like this. And this is the Z axis right here. And let's suppose that we orient a piece of tourmaline in this direction. So I'm drawing it in green because tourmaline tends to be a green colored crystal. So I draw a piece of tourmaline like this, and let us suppose that there is light coming in an incident upon the crystal. And let's suppose this light is coming along this direction. So this is unpolarized incident light. And by unpolarized, what I really mean, that's kind of shorthand for saying that it's vibrating both back and forth along the x-axis and up and down along the y-axis. Technically speaking, it's polarized, it's vibrating in every different orientation in the xy plane, but each of these vibrations can be kind of decomposed into a vibration along the x-axis and a y-axis. Just like if you're traveling northeast, one can talk about it as traveling both east and north. So if we imagine the vibration along the x-axis, I'm going to indicate this by a line like that, and vibrations along the y-axis, I'm going to represent this by a line like that. So that is initially unpolarized light incident upon this tourmaline. And the interesting thing is that this tourmaline crystal has some natural kind of orientation of its atomic structure, or some architecture that is oriented somehow in this direction. And it's not quite clear how this works because we don't have yet a detailed understanding of the atomic structure, but somehow this allows only light that is polarized in this orientation to come through, and as Tyndall says, it attenuates or damps out the light, the component of the light that is polarized in the horizontal direction. Now, the interesting point that he makes is that if one were then to take another piece of tourmaline crystal and orient it in the other direction, and I'm kind of indicating its orientation by the length of the crystal, so that somehow this one is oriented in this way. Now what happens is, since this second piece of tourmaline crystal only allows the horizontally or x-directed polarization of light to pass through, that means that over in this region it is dark, because no light is transmitted. No light is transmitted. This is what he is describing in figure 22.3 on page 261, where you have crossed polarizers, as one would say, or crossed pieces of tourmaline that render the light extinguished in the region where it has to pass through both of them. Okay. Now, he goes on to talk about another interesting effect, and that is how one can have polarized light falling upon a particular mirror or a piece of reflecting material at a special angle called Brewster's angle. And if you do that, you get some very interesting effects. So what I'm going to draw now is, let's suppose that we were to have, and I'm going to once again draw some axes here. Okay, let's call this the x-axis and the y-axis. But now let's suppose that we have light coming in along the y-axis like this. And let us suppose that this is initially unpolarized light. That is, you have vibrations along the along the z-axis. I guess I should label that here. Along the z-axis, and you also have oscillations along the x-axis. So again, this is the direction in which the light is traveling, and because it's a transverse wave, there are vibrations both back and forth along the x-axis and back and forth along the z-axis. Now, let us suppose that one were to take a piece of tourmaline and orient it like this. So I'm going to draw these. Again, it's not like they're actually lines like this, but this is somehow an indication of the crystalline structure, so that when the light passes through this crystal, the only component of the light that passes is the component that is polarized along the x-axis. Now, what does he say? He says, if this light then falls upon a reflecting surface, and let's suppose that this reflecting surface is oriented in such a way that the incident angle, and by the incident angle I mean if you draw a normal to the surface, so that the incident angle theta happens to be Brewster's angle. And we came across this in our lab experiments this past week. Well, Tyndall's going to talk about this shortly. But if we were to have this incident at Brewster's angle, then one would find that the light that is reflected off of the surface, there is light reflected off of the surface, and it retains the exact same polarization. So the light kind of comes in like this, it bounces off right here, and it comes out, and it is polarized in this orientation. Now, so that's just maybe some background. And now I'm going to draw another drawing, the same kind of thing, where we have a y-axis like this, an x-axis like this, and a z-axis like this. And once again, let's imagine we have light coming in this orientation, and it is initially unpolarized light. And again, by that we mean that it's got vibrations along the x-axis and along the z-axis. And now let's suppose that we orient a piece of tourmaline in this way, so that it only allows light that is polarized in this direction, that is along the z-axis, to pass through. So as it passes through in this orientation, the only polarization that gets through is like this. And now, if we let this fall once again upon a reflecting surface, like a piece of glass, let us suppose, and oops, I like to keep my colors the same. Let's suppose it hits it in such a way, once again, that it's incident at Brewster's angle. So this is theta sub b, or Brewster's angle, which he's going to mention is about 58 degrees. Now here's the interesting point that he makes, is that if it's oriented, polarized in this way, there is going to be no light reflected off. So no light that is reflected off of this surface if it's oriented in that way. Why is that? Because remember, Brewster's angle is the angle such that the light reflected off is purely horizontally polarized. And since there is no horizontal polarization of the light that's incident upon the crystal in case 2 over here, therefore there must be no light reflected whatsoever, as opposed to in case 1, where the light is oriented in this horizontal direction that when it's incident upon the crystal, so when it's reflected from the crystal at Brewster's angle, there is light that's horizontally polarized. That's the point that he's talking about on page 261 and 262. And if I were going to kind of develop this thought a little bit more, he mentions that at the top of page 262, he mentions that Malice, a man named Malice, made this discovery in 1808. This is the second paragraph at the top of page 262. He says that Malice observed light reflecting at a special angle from the windows of the palace at Luxembourg. So if I were to imagine, I'm going to use this real estate up here. Let's suppose that we have this window. Oops. I'm going to go back because I messed that up. Let's suppose we were to have this window like this, and draw a window in here. And he looked at sunlight, apparently, and sunlight was falling on this window, striking it, and reflecting off. And if this was incident at just the right angle, that is, this was what is now called Brewster's angle. This wasn't called Brewster's angle at the time, but if it's incident at this particular angle, because the sunlight, I'll mention here, this is sunlight coming in, is both vertically and horizontally polarized. When it comes off, it is strictly polarized in this way, in this plane, okay? And how did Malice recognize this? Well, presumably he was looking with maybe a sheet of tourmaline. He oriented this way and he could see the light that was reflected off this window at the Palace at Luxembourg. But if he oriented it, if he rotated this, then he was unable to see any reflected light. So this is the phenomenon of polarization by reflection. And again, this is something that you studied in lab this past week.